Hello friends, this video on Semiconductors Part 7 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till Part 6 before going ahead with Part 7. Let us now discuss P Type Semiconductor. So once we have discussed the N type, it is easier to understand P type. So in P type semiconductor, we have a group 3 impurity. So a group 3 element would be a trivalent element, that is, it would have a valency of 3. Let us take the example of a group 3 element, say aluminium. So what would be the electronic configuration of aluminium? It will be 1s2, 2s2, 2p6, 3s2, 3p1. So that means in the outer shell, that is the shell corresponding to n is equal to 3, we have how many electrons? Valence electrons is 3. So we have 3 valence electrons. So what happens in this case? This is my aluminium impurity. So it has got 1, 2 and 3 valence electron. That means it has a shortage of 1 electron, right? Because there is one, it should have one more electron. So what will happen? If it does not have one more electron, that means it has a hole. Absence of electron is a hole, right? So that means if you look at this impurity, it has got 3 electrons which are involved in the covalent bonding, and there is one hole. Now since this hole is empty, the electron from surrounding, let us suppose this electron jumps here, or you can think it in this way, that this aluminium atom snatches one electron from the neighboring atom. So this electron comes here. So a hole is created here, right? Now what happens as soon as this aluminium atom gains one electron, the aluminium becomes a negative ion because it is taking one electron from outside. Before it was neutral. Till now it was neutral, but as soon as it takes one electron from outside, that means it is taking an additional negative charge. So it becomes negatively charged. But since it is involved in the covalent bonding, therefore it cannot move even though it is a negative ion, but it cannot act as a charge carrier because it is immobile, because it is fixed at one place because of the bond formation on all sides. So this aluminium atom becomes a negative immobile ion. However, the holes which get created, for example, this hole is created when the electron jumped here. Again, in order to fulfill this hole, some electron jumps from here. So a hole is created here. So that means this hole is moving in one way. So this movement of the hole gives rise to a current in this case. So that means in this case, we have additional holes. Like in the previous case, the impurity gave us electrons. In this case, the impurity is giving us hole. So in this case, the impurity is known as an acceptor impurity because the impurity is accepting an electron from the neighboring atom. So that is why this is known as, so I'll just note it here. So this is known as acceptor impurity, right? So in this case also, when the temperature, so this happens at room temperature. At room temperature, these extra holes are generated. But when the temperature is increased, thermal energy is provided. Again, the same process of electron hole pair generation takes place. So that means those electrons and holes are generated, but in addition to that, in this case, extra holes are also there. So number of holes in case of a p-type conductor is greater than that of the number of electrons. And what was another thing to be noted here? Here the impurity, here two things are to be noted. One is the impurity is an acceptor impurity because it snatches electron from its neighboring atom. Therefore, the impurity becomes a negatively charged immobile ion. So here we have a negatively charged immobile ion. Correct? But the holes which are getting generated, these movement of the holes give rise to an additional current at room temperature. And that is how semiconductors conduct at room temperature. Fine. So how will the energy band structure look like in this case? So in this case, we will again have an additional energy level, but this time it will be near the valence band. and we denote it as EA, that is the acceptor energy level. So who will reside on these energy levels? So in this case, what will happen? Here you have your electrons and holes. Now the electrons, the extra holes which are getting generated, they will come to this acceptor energy level where the electrons will get excited very easily. I mean, electrons to excite from this EV to EA, they need very small amount of energy which they get at room temperature. So electrons will come at this energy level EA. As a result, a lot of holes will be created in the valence band, and the movement of these holes in the valence band will give rise to the additional current. Whenever I am talking about additional current, I am talking about the current which is in addition to the current which is thermally generated. Right? So right now I am talking about the room temperature current. When you are at room temperature, there is no thermal generation of electron hole pairs. So at that time, these excess holes in the valence band give rise to the current. Right? So in P type semiconductor, number of holes is greater than the number of electrons. Majority carriers in this case is holes. Minority carriers in this case is electrons. So if you look at the energy band diagram in this case, you can see that this is the acceptor energy level. Since the electrons tend to move towards the acceptor energy level, a lot of holes are created at the valence band. So because of this movement of holes, you get some additional current. Right? So far clear? So till now we discussed about the types of semiconductor. Extrinsic semiconductor, which is the impure form of semiconductor where we add impurity to increase the conductivity. And the second one was the intrinsic semiconductor, which was the pure semiconductor. Right? So now you understand what are semiconductors. I think it is getting clearer now that semiconductors are such objects which do not conduct electricity always. They conduct electricity. I mean, you will have to do something so that it conducts electricity. Either you can add impurity to it, or you increase the temperature and provide some additional energy. But if you give some effort from your side, the semiconductor can conduct electricity. Right? So let us quickly compare the energy band diagram of N-type and P-type. In case of N-type semiconductor, we have additional electrons because the impurity in this case is a donor impurity which has extra electrons. So because of this, we have a donor energy level. So electrons can very easily jump from this level to the conduction band. Whereas in case of a P-type semiconductor, we have impurity which is of acceptor type, that is, it accepts or snatches away electrons from neighboring atoms. As a result, holes get created, and this movement of the holes or this generation of holes give rise to so many holes in the valence band, and also an additional acceptor energy level is created where it is very easy for the electrons to jump to this level. So here in this case, in addition to the thermal generation of electron and hole, you have additional holes, and this results in additional current. Now, what happens, and it had been approximately found, I mean, some experiments were done, and using some data, it was approximately found that at equilibrium, number of electrons multiplied by number of holes gives square of intrinsic carrier concentration. However, this result is an approximate result, but it turns out to be true in most of the cases. That is, number of electrons multiplied by number of holes. I mean, when we talk about an in case of an extrinsic semiconductor, the number of electrons multiplied by number of holes is equal to the intrinsic carrier concentrations square. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.